So what I have there is just vegetable oil. So one of the most important things that we need to understand is this concept called index of refraction. So index of refraction basically tells you how much the speed of light changes when it goes through a different medium. So when we talk about the speed of light in 3.00 times 10 to the 8 meters per second, and this is another one that don't think about this too much or you'll just end up down a rabbit hole of pain and suffering. So that 3.00 times 10 to the 8 meters per second is technically in a vacuum. Now, we don't live in a vacuum, thank God, because we couldn't. We do have an atmosphere, but our atmosphere, the air molecules, as some people like to put it, don't slow down light appreciably, okay? So unless you're told differently, even in our atmosphere, you can assume the speed of light is 3.00 times 10 to the 8 meters per second. Okay, now, but that's as fast as it can get. If you're going through any other medium, glass, diamonds, cooking oil, whatever it is, light slows down. So the more optically dense something is, the more it slows down. Now, don't ask about how it slows down. Okay? Just for now, just accept it that it does. Like, whoa, what? Does it hit the brakes? What does it do? Then when it goes back out, does it speed back up? Do they have like little the photons have like brakes and gas pedals and they hit those as they speed up and stuff? Okay, just accept it. Just accept it. Just accept it. So, if you think about what has to happen for you to see through this test tube. So here's this test tube full of air. So Joe photon is traveling through. So if you look at the mechanism that has to happen, for me to look through here and see all of you through here. So the photon has to be emitted from the light. Light's going to come through here, and then it's going to travel through the glass, okay? Then it's going to travel through a gap of air. Then it's going to travel through another gap of glass. And then it's going to go through a gap of air, and then it's going to hit my eye. Now, for you guys, if you were to look at me, okay, so if you look at this, then for you to see me, that light is being emitted, it's hitting me, it's bouncing off, it's going through the test tube. So if you're looking through the test tube looking at me, the light has bounced off of me, it's going through here, and now. So there's a couple ways you get index of refraction. One option is that you take the speed of light and then you divide it by the speed in the new material. So let's look at this. So let's say the speed of light in your vacuum is 3.00 times 10 to the 8 meters per second. So let's say that you know that the speed in a different medium might be, I don't know, 2.50 times 10 to the 8 meters per second. It's going to slow down. So if I take 3 and divide it by 2.5, first off, am I going to get a number bigger than 1 or less than 1? Bigger. So even if you divide by the speed of light, what's your index of refraction going to be? 1. So even if the speed of light in that new medium is still the speed of light, you get an index of refraction of 1. So the biggest index of refraction you can get is 1. Okay? Right? Excuse me, the smallest index of refraction you can get is 1. The smallest you can get is 1. Now, if I take 3 and divide that by 2.5, somebody take 3 and divide it by 2.5.
1.2.
What'd you get?
1.2.
1.2. So this would be an index of refraction of 1.2. So the smaller this number gets, the velocity in the new medium, what's going to happen to the index of refraction? It gets bigger. So the more it slows down, the bigger the index of refraction is. Okay. So I'm going to take this test tube. We're going to put it into the cooking oil. Now, this gets even more complicated. So for you to see it, the light, like for me to see this, so the light's coming from the source. It's going through the Pyrex beaker. It's going through the oil. It's going through one side of the tube, through the air gap, through the other side, through the oil, through the Pyrex to my eye. Okay? This is a long journey. Okay? And each time it's either speeding up or slowing down. But now I'm going to take the test tube and I'm going to fill it up with vegetable oil. Okay? Just hold on. Okay? All right, so watch the test tube. Okay? Focus on the test tube.
Why is it disappearing, Mr. Burkamp? Why is it just going away?
Oh, now we got 2D.
Yeah, and the electrons know when you're watching. Mr. Burkamp's just gone, buddy.
So, what happened?
It's just gone now.
It disappeared, obviously.
I think.
It disappeared.
So this
It's
is
no
how
longer
it
there.
What an
Can we not just believe in magic?
Huh?
Can we not just believe in magic? Like, do we have to really figure this out?
We really have to do everything.
Because the entire
Easy. Janet's trying to sleep.
I'm not working.
So,
Wait, Berg, does like say diamond have a bigger in value than oil?
yes.
Okay.
Okay? So what makes diamonds diamonds is diamonds have a very high index of refraction, which means they slow down a lot.
Really?
Yes, that's why we'll get into how it bends like later. So the reason that it appears to disappear, because up here you can see it,
It's
see?
just
Okay, is because of the fact that oil and Pyrex have the same index of refraction. So as the light goes through the oil and the Pyrex, since it's the exact same index of refraction, nothing changes. It doesn't speed up or doesn't slow down. So that's why it appears to disappear. Because the light can't tell the difference between the two of those.
So the oil and the glass have the same in value.
Yes.
All right.
Oh, okay. Now it makes
All
sense.
right.
Now
Right.
you connected the dots.
Can we add more oil to it?
My brain's still exploding right now, but
Well, if you just fill it all the way up.
So if I can have the same condition as air, I can use this.
Yes.
wait. So if you just drop that whole glass in, how do
Yeah,
I
yeah, yeah.
squeeze it?
So now,
I still see it. I can still kind of see it.
No, you can't.
Yeah, I
No,
do.
you can't.
There's
No,
like
you
a
can't.
little faint outline.
No, you don't.
Yes, I do.
No, you
Right.
don't.
I still see it.
okay, you can kind of see the faint outline of it.
No, you
This
But for the
isn't
most
magic.
part,
No,
but you can kind of admit that it basically disappeared.
It,
Okay. Now.
That's gone.
Okay. Now we need to combine some different equations.
No.
One is E equals H nu or H frequency, depending upon how old school you want to go. So, this is going to be so important later on. Okay, I'm just laying the initial
There
ground.
goes my A.
This tells you the energy of a photon, whether it's a microwave, red light, purple light, whatever. This is dependent upon Planck's constant. It's just a number for now. Don't worry about it. It's just Planck's constant. And this is the frequency of light. But the energy determines color. Okay? The energy determines color. Now, so if I look out and I see, okay, Gavin's kind of wearing a red shirt back there. Okay? So if I put on my glasses, or if I don't have them on at all, that still stays the same. Okay? Doesn't matter. So what this means is that when light travels through this thing and it goes through that glass, okay, this glass makes it slow down. It also makes it refract, which is what makes it go into focus, why you wear glasses. So that light speed is changing as it goes through the glass. But here's what's important. It still shows up as red. So what that means is that even though the light slows down when it goes through my glasses, it maintains the same energy level. Okay, this is important. It keeps the same energy. So, speed of light is wavelength times frequency. So when you go through a different medium, okay, you get a V instead of the speed of light. The reason that I know the frequency stays the same is because the color stays the same. So listen to me. Energy is determined by frequency. Now, think this through. Let's say that that was the speed of light, 3.0 times 10 to the 8th meters per second. This is 2.50 times 10 to the 8th meters per second. So what's happened to the velocity? It's gone down. But I had the same frequency. And I know that I had the same frequency because it's the same color, because it's the same energy. So if frequency stays the same and velocity becomes smaller, what's the only way that can happen?
Wavelength.
Oh, so the wavelength of that light becomes smaller with a higher index of refraction. And the bigger that index of refraction is, the bigger the drop in the velocity, the bigger the drop in the wavelength. So this is important. Frequency stays the same. And here's how I know that frequency stays the same. Whether I'm looking at Gavin with my glasses or without, it's the same color. Because if frequency changed, this would get really weird, then when you would look through like your car windows or you look through glass, colors would change. Because you change the frequency. But conveniently you don't. The frequency stays the same. So,
What's a rainbow?
Bro.
This has me questioning about like 20
Yeah, he said not to think about it.
Oh, you're right.
The only thing about it is you're not going to do my homework tonight.
That's a good idea.
That's valid.
okay.
I look
Now,
agree.
here's another hint you gave me little
What
equation.
is that?
So, the wavelength in a different material is the wavelength in a vacuum, which would be the longest possible wavelength, divided by n. So as n gets bigger, what happens to the wavelength in the new material? It becomes smaller. Notice that we don't change the frequency. Why don't we change the frequency?
Because the
We
color
don't
is
change
The
the
color.
energy. Okay. Whew, that was a lot.
Oh, thank God.
Okay.
This is a color.
So,
Praise the Lord.
pretty short assignment. This is out of after chapter 17.
You're gonna give us 30 questions.
No.
You got me, right?
Praise.
You got me.
Oh my gosh.
If you call me while I'm on
CV 7 minus, that's the charge.
I don't want to do this.
7 minus.
I never signed up for
Are you going to do your read on Saturday?
They got me, guys.
this.
Oh, Tuesday.
Cool.
We're going to go to Hudson.
No, those
Where's
are
the
same.
time?
What?
Campus school ain't that. It's in the bottom of. It's in the top of school. It's in the top of school. So yeah, you can go to like.
Well, campus stinks of food, which means
Campus doesn't have a bad pool, guys.
which means the pool has been heated.
All the pools are competing, Gavin.
Stop.
Wait,
That's it.
you gotta watch the Montreal video.
No.
Tetrachlorine, buddy.
No.
Tetrachlorine, buddy. The real thing. Beware.
I know that you, the biggest topic.
Mr. Bergen knows what I'm talking about. At least. Yes, he does.
It'll make sense when you get to that problem.
What do you mean just leave the green?
As in like.
You just said it'll make sense when you get there,
I don't
Peter.
want to get there.
You gotta get there.
Why skip?
So you don't go to the internet and find different values. On page 538, there's a chart that lists the index of refractions that I want you to use. Do not go to the internet. Do not ask Google. Do not ask ChatGPT. Look in your book to find those indexes of refraction. Okay?
Oh, no,
Okay.
my friend is saying this.
Why did we get there?
What is it?
Chapters at this point.
Is this on our test?
Wait,
Burkamp.
Burkamp.
Burkamp. Is this on our test?
Yeah.
No, it's not.
You don't have them anymore.
Yeah.
Wait, there's no study guide?
No, like you're going to work through a bunch of problems.
Oh, okay, good.
Oh.
What if we don't have school tomorrow?
Wait, Burkamp.
It like has all the.
This all sounds very cool.
Like, is that what it's gonna be? Yeah.
Look at these pictures. Look at these ugly pictures.
Yeah, your textbook might have a pool.
I'm gonna cry.
Burkamp.
Look